Thank you all for coming on the week of Thanksgiving. I'll accept it as my birthday present from you because yesterday was my birthday. So there you go. Everyone else still loves me. As Mark mentioned, I'll be talking about cooperative communication as belief transport. And I'm going to give sort of a non-standard view of the sort of field of machine learning through the lens of human learning. And sort of try to push, I think, from a slightly different direction than you might have heard before. And so I'll spend a lot of time motivating the problems because I think the whys matter a lot. And then for the second half, we'll show some very basic mathematical results, formalizing some of these ideas. So human learning is distinctive in at least three ways relative to the state of the art in machine learning. So humans are able to learn rapidly and robustly. And so by rapidly, I mean with small amounts of data, relatively speaking, and robustly, meaning in the face of great uncertainty. And I'll talk a little bit about the relevant uncertainties for this talk, but of course there's a bigger context there as well. They do so in an effectively open world. And this is important because much of modern machine learning succeeds by making the world really small. Right? We're going to classify dogs. And even though that's a huge world, like that still massively undersamples the realities one can experience. It also raises questions about sort of relevant theoretical frameworks. So a lot of the way we think about statistical estimation is by convergence in the limit. But it's not entirely clear that convergence in the limit is that useful or relevant as a model for thinking about learning, at least on a human level scale or many agents, human or otherwise. And they do so in what is almost real time and with little energy. So, for the most part, much of human learning goes on just as it's happening right away. Of course, many things are protracted over time, but we're learning at all moments. We don't take breaks to sort of think for long periods of time and don't process anything. In the same way that sort of, if you ask a computer to calculate something, it goes away and then waits for a little while and comes back. They do so with very little energy in the sense that, all of what they're able to do fits inside a human head without lighting on fire, right? In contrast with a gigantic server farm that needs massive amounts of cooling in order to stay viable. And so these together, I think, sketch out a sort of different picture of the problems of machine learning in some directions that it could be moving than what one might see more standardly. So today, what I'm going to focus on is this first point, rapid and robust learning, and I'll leave the others to some other talk, which may be part N of the, if people are interested. And so, you've probably heard or seen in various forms the basic idea of artificial intelligence, which has been for the past 70 or more years about individuals. So can we make individual machines that can accumulate data and draw accurate inferences from those data? But in the past 20 years or so, there's been a shift in a variety of literatures away from that picture of learning and the power of human learning toward a picture of being situated in a context of social context, I should say. So if you look at cognitive development, a lot of the modern emphasis is on the ability to transmit knowledge from parents to children or between conspecifics more generally. Education, of course, is a great example of this. In cultural anthropology, people are interested in explaining how people accumulate knowledge over generations in a way that other animals seemingly do not. And they often talk about other people's role in ensuring that. And in robotics, this is viewed as a model for making sure that humans and machines can cooperate and coordinate, but also as a way of creating teams that can learn and adapt to situations as they change. And so across all of these literatures, people have settled on this idea, for now anyway, that cooperation between conspecifics is a really key element. And in particular, cooperative communication, because it gives us a way to transmit knowledge between individuals without having to go through the entire process of deriving that knowledge necessarily oneself first. So my goal today is going to be to convince you that we can take that relatively squishy idea and formalize it mathematically. And we can use that math to do some basic stuff, prove some basic results about how cooperation should behave. And I think hopefully it will be evocative of a much wider set of results that we could actually go after if we so desired. So for today, I will follow basically a three-step plan. I'm going to spend a bunch of time giving motivation. So I'll give 3 examples of the kind of phenomena that I think are interesting and relevant here. Then I'll talk about the protocol or algorithm that people have proposed in the various literatures that I've mentioned. Then I'll talk about how it translates into a mathematical perspective. All right, so. So the 3 examples. These are going to take the form of games, so I hope people will participate. The first one is called hat and glasses. This comes from linguistic pragmatics. So we've got 2 people, one with hat and glasses. The second game is called rectangle game. And there's going to be a board, and we're going to play a game where I try to think of an axis-aligned rectangle, so something like this or like this, and teach you by way of points where my rectangle is. And then the last one is what I'm going to call nodes and links. This is a fun experiment because I've never done it with people before. But I'll be able to blame someone else if it fails, which may or may not be popular. And I'll tell you a little bit more about that one in a moment. So to get on with the first example here, suppose we're having a conversation, right? And I am letting you know, telling you about someone who's done something especially scandalous, and I say, so who am I referring to? Am I referring to this one or this one? Who votes number 1? It's the guy with the hat. Oh, sorry. Who votes for number 1?
Number 1 is this side.
Yeah, this one. All right. That's basically everyone. Number 2. All right. This is interesting, right? Because obviously my statement was ambiguous.
Yeah.
But there's a very easy reasoning process to go through to disambiguate it. So this is very common in natural language, that what you say underspecifies what you mean, and the other person, the listener, has to make some guesses, put things together. Here's another one. So this is the rectangle game. And so this comes from sort of the concept learning literature, also appears in robotics, different kinds of referential games. So I'm going to think of a rectangle somewhere on the board. Remember, it's an axis-aligned rectangle, but it could be anywhere. Right? I'm going to think of my best examples. All right. This one and this one are inside my rectangle. The question is, do you think it's a big rectangle, something like this, or a small rectangle, something like this? Who votes big? Who votes small? Excellent. We're winning so far. So people in general, if you ask them this question, they succeed on this task. And again, it's ambiguous, right? That's what's interesting here, is that you know, these examples are totally consistent with this rectangle, but nevertheless, we have no problem figuring out what the other person is thinking.
When you say people, do you mean random people? Or I bet if you did this with mathematicians, you would get bad answers.
You're not far off, yes. So if you survey mathematicians and computer scientists, they do less good. But you're all succeeding, so you know, you're some special mathematicians, I guess. All right, so here's the last example. So this is an example of a concept that I want you to guess about. And so I'll give you other examples. As I said, this could be unpopular, so this is a little exciting. I'll give you different examples here. Drawings leave a little bit to be desired, but they're nodes, links. So votes for number one.
Wait, what are we supposed to say?
So which one is the same kind as the one on the top? What am I trying to sort of convey? This is an exciting one. So who votes for number one?
Each one is the same.
Yeah. Picture is not good enough here. It's non-trivial, so I'm sort of interested to see if it works. Oh, there we go. Single examples are harder than pairs for reasons we've seen. Any guesses?
Can we say none?
No, there is one here. It's a little underspecified.
Answers to the Zoom audience afterwards, please?
Yes, I will.
Because we
So-
actually missed the first two. We don't know what the audience voted.
Audience does this, and the small one. So we're succeeding so far. Any, yeah. Who votes one? People are going with one. Three.
I vote for the minute.
I don't understand the question.
Okay. No, all right, so there's a disagreement. All right, I won't, but, okay, so I'll say a little bit about these. So we saw this one, right? It's underspecified. You need to sort of add something in. Also underspecified. You need to add something in. We had an easy time with these. This one is a little bit, sorry. I actually.
That's why I didn't like
Okay, all right, now.
No, we all.
Everyone votes for one. All right. This would have been bad because it came from a very nice book here.
Was that part of the experiment?
By a guy named Peter. It's example 0.1 for a complete graph. But I stripped away lots of the other details, so that would have been. But you should take solace in knowing that if people render it correctly, everyone knew what you meant. But the point being that these kinds of examples come up in math and in education generally, right? We come up with examples that are meant to stand in for whole concepts, and obviously they're specified. They're going to enumerate the possible set of examples, but they pick out ones that are hopefully good. That makes sense. And so we're able to do this, and it's by thinking about what the other person could have done and what they chose to do. All right, so when I say rapid and robust learning, what do we mean here? So take the rectangle game as a nice example, right? So with two examples, everyone can draw this inference quite strongly and robustly, in this room anyway. Logically, we require at least 4 more to box in the sides on the outside. If we're waiting for those to happen by random sampling, it's going to take a very, very long time. So over and above what it would take in order to learn this, from random sampling or from, or logically speaking, we can draw these inferences by leaning into what we know about other people. And that's the kind of thing that we want to formalize here. This is also invariant under dimensionality. So 2 dimensions, 3 dimensions, 4 dimensions, 2 examples.
Excuse me, you actually mentioned that the middle one is for robotics. Is that what a robot would do as well, or would it depends on how you program it?
It depends on how you program. So I mentioned it is it's a kind of reference game, right? And so the idea here is I give you a couple of points and you have to draw a rectangle. But if I give you a couple examples of animals, you need to draw an inference about whether I'm talking about dogs or cats or mammals or all animals, right? Like there are lots of these games that have similar feeling to them. Other games with geometry also sort of have this feel like pointing.
And you mentioned the first one is natural language. So would this one be computer vision then?
It could be, yeah. I mean, I don't think they're meant to be in a box per se, right? And that's kind of what the point is that they're an instance of a very broad class that appears across a variety of literatures. And that's why I think they're interesting.
Okay, thanks.
So by rapid learning, we learn with fewer examples than we otherwise would. And by robust, what do I mean? Well, I don't know all of you that well. I certainly have misconceptions about what kinds of things you do and do not know. But nevertheless, we're able to pull this off, right? At least if I can write the example correctly. And so we can see that the ability to reason about other people and use what you know about them in order to learn is quite powerful. More powerful than learning by itself almost. All right. On our way to sort of trying to write this down slightly formally. We're going to think about things like data. They're going to be in sets, and hypotheses also in sets. So we're thinking of discrete, finite, just to make our lives easy. We could talk about generalizations, but I want to sort of keep most of the mathematical complexity out of the way. So up here, what we're thinking about our data are things like our hat, our classes, and our hypotheses. This person or that person. We can do something sort of similar here where we've got our board, examples there. Another possibility is that we have examples there. There are many others, of course, that we could enumerate, but it's simple. Being strict, we can't enumerate it because it's on here, but that's fine. We'll play along with me, I think. And then we can do something sort of similar where we have data here as this possible set and maybe some others. And then their extensions being things like complete graphs or same number of nodes or same number of links. Or other concepts that you might think are interesting and relevant. So we can start walking toward formalizing these kinds of things. You can see that there's some gaps that need to be filled in a little bit in cases like this and so on. You have to sort of make some choices, but let's not get too worried about those just yet. All right. And so what we want to do is talk about, well, what is the structure of this game that we just played? Okay. So structure of the game is something sort of like this. So we're going to draw a hypothesis from our set of hypotheses with some probability distribution. The teacher is then going to, and we'll call it a teacher. I'm not necessarily meaning to invoke education per se, but just to have a name for the two players in the game. We have data that are drawn. Conditional distribution where they take in the hypothesis and they need to sample data. Then we have the learner draws a hypothesis conditional on the data they observe. And then, of course, we decide whether we're successful. That's if the original hypothesis is the same as what the learner draws.
What is that, number one? That represents the teacher's.
The hypothesis comes from somewhere, right? And we're gonna, for now, say that it comes from the learner's prior beliefs. So,
Oh, that's the learner's
Yeah.
prior beliefs.
so yeah, I've introduced a little subscript without talking about it, but yeah.
And sorry, the next one was P teacher.
Teacher, yeah.
Okay.
I'll talk about those right now, actually. All of the action here, and I told you what happened. I didn't tell you the interesting part, right? So you can see that this is just a one-off game where, we have a hypothesis, we either get it right or wrong, and so on. But what's going on in here, right? How do we define these two things? One sort of straightforward way to start is to start with the learner. I say it's straightforward because you may have heard that people have thought about problems where you update hypotheses given data before. For example, Bayes' theorem gives us a prescription for updating one's beliefs given an observation of data. That's going to be in the numerator related to your prior beliefs about the hypotheses, the probability of the data given the hypotheses, and then a normalizing constant to make sure everything sums to 1. You'll notice that, as Akshay already pointed out, I've introduced some subscript with these, and that's the difference here, right? Is that we have two agents, a learner who's contributing 2 pieces and a teacher who's contributing 2 other pieces. We'll talk more in a second about this. Obviously, the key thing here is to sort of specify where this is coming from. Right? And so if you're doing standard Bayesian modeling, you would assume something like a normal distribution or some distribution that sort of gives rise to the observations. Right? So normal distribution being a standard choice, but in many contexts, you could adopt many different choices. Here, what we want to do is formalize an agent, right? This thing that we're calling a teacher. And we want to specify how they're going to sample data given a particular hypothesis. And we can do that relatively straightforwardly by just turning all the variables around, right? So we've already seen that the teacher is going to sample data given a hypothesis. So we can say that the learner, how are they going to do that? Well, they're going to choose the data such that the learner tends to go to the right hypothesis. Weighted by the teacher's prior probability of picking data, so maybe a preference for fewer data points or less complicated situations. And normalized. And so you can see what we've done here, right? So we've got the learner reasons about the teacher reasons about the learner. If we can make some assumptions about this situation, then people can reason about each other independently. So those assumptions are going to be around this piece, and a piece you don't see, which we're going to call M, but it's going to allow us to derive these two. And the basic idea here is if the learner knows, of course, their own prior, which doesn't seem like a big assumption, but the teacher's prior on data also, and some common knowledge about the situation, right? And so you might think of this as sort of the consistency of the examples with the different concepts is a sort of general way to think about it, but we might think about it more mathematically as any non-negative matrix, and so it could be weighted consistency. And to get from here to here, if M is going to be Mij n by M, and we normalize down the columns. So we're thinking about it as a data on the rows and hypotheses on the columns matrix. Then we normalize down to get this, and we normalize across to get that. And then everyone can sort of go on their own and solve these things independently. And you would do this by plugging in, if you're the learner, your first guess about the teacher. Update your belief, ask how the teacher would update their belief based on what you're doing, and so on. And we go through this fixed point iteration, which provably converges. So more about that in a moment. Okay. And this is really fairly directly implementing the ideas that I think everyone had in their head, right? Which is that you're thinking about, well, why did the other person do this? Based on what they did, here's how I should update my beliefs.
How is the RAM established?
Yeah, so this is assumed to be common knowledge ahead of time. And we're going to come back to that because these common knowledge assumptions are big, obviously, right? And perhaps a little unsatisfying, but we'll come back and talk. So if we want to sort of play this out, let's see. Maybe I'll go this way. We can actually do some hand calculations just to sort of make sure everyone's on the same page here. So we can say for the hat and glasses example, we're going to make some simplifying assumptions to make life easy. These are going to be some constant, we'll call it A. So uniform distributions, right, on those things. And so this and this are going to drop out. And then set up our M matrix, right? So this is hat, and this is glasses. This is going to be our M matrix. Glasses. See, consistent, not consistent. He's wearing a hat and glasses. And if we want to take the learner's perspective first, we want to plug this M in and then normalize along the rows. So they have a conditional distribution conditional on the data, right? And so sort of step one, you would do is you need to compute the denominator, which is just the sum over all the hypotheses, right? So use of basic marginalization. We can sum here, and then we get half 0. That's from the learner's perspective. Then we can go to the teacher's perspective, T1. Let's call it T. Here. And we can keep going along these lines. And you get the feel for the fact that this is going to converge. It's going to take infinite time. It's going to decrement by 1 each. It will converge, and the converged solution will be, the interpretation that everyone arrived at. Some sort of a feel for how these models work. So this is one model of this kind of approach. I'm using it to stand in for a family of models, which vary primarily in the number of recursive steps you might posit, as well as exchanging this probabilistic sampling for a greedier version of sampling sometimes. But they're all of the same ilk. I'll try to. You can come back and ask me questions about that, but they're all approximations to what I'm going to say next. All right. So I think we're in good shape here. So this is the sort of state of the art as of about, I don't know, 5 or so years ago. People have been proposing a variety of models along these lines. But a characteristic of all of these models is that you have to specify a situation. and run all the calculations. So they're algorithms really for getting predictions. And what we lack was any reasonable way to sort of formulate it in a way that I could say something about all possible scenarios, which is of obvious use in human robot type situations, but also as predictions about sort of people and so on. Want to be able to understand our scientific theories, also any implementation that we're going to set up. Be able to put some guardrails there or say what is or isn't possible given certain assumptions. And so for the rest, of my time, I'll be trying to convince you that there is in fact a very natural way to think about this in terms of optimal transport. And so sort of more specifically, so this probabilistic cooperation picture that I've been saying, some minor caveat here, exactly what's an algorithm called Sinkhorn scaling, which is a method for solving entropy regularized optimal transport. And that's going to be the whole picture. Let's say just a little bit about OT and EOT, and then we'll sort of make this connection. So we're going to think about vectors.
You're mentioning their belief transport. Is that the same as belief propagation or?
No, quite different. Yes, good question. So belief propagation is a method for usually approximate inference used Bayesian settings. Belief transport here is sort of a merge of the two names, right? So we're thinking about transmitting beliefs through cooperative communication, and the formulation mathematically is optimal transport. So, thanks. So again, we're going to still keep ourselves in sort of a simple world. We're going to think about row vectors and column vectors. These are going to be probability distributions, so they all sum to one. We're going to think about joint distributions or transportation plans. Which are going to be n by m, and they're going to be non-negative. The set of transportation plans is going to be notated URC, and so this is set of plans with marginals R and C. So in general, there is going to be more than one plan. All right, and we're going to assume we're given a cost matrix. It's also going to be non-negative and live in n by n.
It's symmetric?
Not necessarily.
No, it's not.
So the formulation of EOT.
Question was that.
Yeah, n might not be.
It's not even a square metric.
It doesn't have to be a square matrix.
Yeah.
But we knew what you mean. You see, that's exactly what we. All you matrices is rectangular.
So we're going to be looking for an optimal plan with a parameter lambda. It's going to be argmin p in u rc. where this is the Frobenius inner product, so it's just the product of the elements summed up. And so this piece right here is optimal transport. Ignore this part. You can see that obviously. If we send that to infinity, we reclaim optimal transport. But in general, we're going to think about having this entropy regularization on the end, where entropy is the sort of standard definition of entropy. So it's P log P element wise. Right. We're going to call this thing Sinkhorn plan.
Sorry, do you know how old this is, this Sinkhorn that you're talking about? When was it
1964, Richard Sinkhorn, and then 67, Sinkhorn and Knopp. But similar ideas have been all over the place. He proposed in mathematical statistics, but similar ideas were proposed in standard statistics. I haven't made it clear, but you can probably guess that it's closely related to a chi-square distribution in interesting ways. And so Good and Callback published on it more recently. Cesar did a bunch of work. It's a little bit related to Schrodinger bridge type problems also. And so there's sort of an older history in that direction. Anyway, the idea is very simple and has been reinvented many times.
Okay, thank you.
Yeah, that's a good question.
I think obviously Vigderson's worked with this.
Yes. Yeah. Avi has a bunch of work also. Not in 1967. All right, so we're going to call this thing a Sinkhorn plan, right? And the Sinkhorn plan is going to come from the fact that we obtain it by Sinkhorn scaling. And so to sort of see this and the connection to a broader world, let's see if I can give you a little sketch of the picture. But the basic idea is that this, with entropy regularization, has a unique solution, and it's going to be of the following form, which is, I think, beautiful. So I is going to be J. Guessed from other context. The form is going to be like so. So this is going to be our optimal plan. This is going to be the Gibbs kernel. And so we obtain J e to the negative lambda cost. And then multipliers on rows and columns. And you can sort of see where this is coming from the other examples, hopefully. To actually, set this up fairly precisely, we would want to introduce, so Sinkhorn is going to be the dual formulation of entropy regularized transport. So we're going to introduce some two vectors f and g in our n plus and our m plus, so they're positive vectors, and formulate the Lagrangian. Here. Second. And set equal to 0 and solve. So from here, we can multiply through by this, move things around. Did I drop? Well, yeah, to move things around and then exponentiate to get Bij. It's going to be e to the f c e to the negative c j e. And then, yeah, it's a simple change of variables to get back to our original version. One of the things that you might recognize, if you're familiar with this literature, is that you can also see this as an instance of a DAD type scaling problem, where D and D are diagonal matrices. A is going to be. So Sinkhorn solves for entropy regularized optimal transport. That's the first bit of the story. The second bit of the story is to say that probabilistic cooperation is exactly Sinkhorn. That might be sort of clear already, but I'll be very, very clear. I'll do it out. So we're going to, in order to show this, we're going to look at the fixed point for the cooperation, and we'll see that it's basically the fixed point for Sinkhorn scaling also. So to do so, we're going to take our standard Bayesian formulation, multiply on our original constraint. Seems given and mutually known. We're going to put it on both sides. See, it's here and here. And we'll do the same on the for the other equation, but in the opposite. So we're going to have P of L0 H. Then we can take this and put it down here. Or kind of move. And observe that this is this, and this is this. And when does the fixed point occur? Well, when this is the same as this, and this is the same as this, which is exactly when the fixed point occurs for Sinkhorn scaling also. They're literally doing the same thing. All right, so Sinkhorn scaling is EOT. I showed you that probabilistic cooperation is Sinkhorn scaling for lambda equals 1. It's straightforward to generalize to the more general case. You just have to exchange, just have to introduce the exponential in there.
Sorry, I think I missed the definition of what is Sinkhorn scaling?
Yes.
I think you said it, but I just maybe missed it when you said it. What's
Sinkhorn scaling, I said it, but I didn't write it down. But it's just iterative normalization of rows and columns.
okay?
Right, so you take a non-negative matrix, you sum up, say, the rows to start with, by symmetry of the columns, divide through by the sum, and multiply by the marginal, whatever you want it to be. Right? Whatever the specified marginal is in this case. And you do that.
Certainly one of Avi's favorite.
Yeah,
It
obviously.
certainly made a living.
Quite a bit of work on this. Yes. So where are we?
And sorry, in this context here, you're saying if you apply Sinkhorn scaling to something, you end up with this optimal Pij. Is that right?
Yes.
Okay.
You apply Sinkhorn scaling to the K matrix, right?
Which
E
is
to the negative lambda. Sorry, I erased that part. That was
e to the lambda Cij.
yeah.
Okay. Okay.
Yes, it converges quickly. It's like easy.
Sometimes. I gave an example where it takes infinite.
No, but I think it's exponential.
Yeah.
So the cost is the sort of the logarithm of the rows in your original M matrix.
Yeah, so if you think about starting from a probability, then you take negative log of the probability, and that will get you your cost. Or you could use utilities directly or distances, or and all of those. If you're thinking classic OT, it's distances. So yeah, so what's interesting or exciting about this? Well, so we've shown that this thing that's been proposed a bunch of different times in behavioral science, mostly literatures and some machine learning, is equivalent to a nice mathematical object about which we know quite a lot. Sinkhorn scaling. Sinkhorn scaling is, for example, a continuous function. It's homeomorphism. There's a lot out there. And that is solving for entropy regularized optimal transport, which is itself attached to a huge mathematical literature on optimal transport. And so we can go and use some of those techniques to answer questions about the original models. But I think, and then we can also go and ask, well, in what ways would we want to extend it in order to better capture these models? And so I'll give a little bit of an example of the former, and I'll just not even talk about the latter because I think that's interesting. But
So did you say that once I put in the entropy regularization, then I have a unique solution?
yes, yeah, strong convexity of entropy
Okay.
gives you a unique solution. In general, it's not unique without that. So given time constraints, I'll sort of wave my hands at the 2 points that we started with. So the rapid learning. So I've given you the intuition for how that's so. You can actually go through and make that more formal by looking at the problem as an estimation problem. So if you look at the learner's posterior, right, P of H given D, sort of vanilla Bayesian inference, well, let me take a step back. So one sort of indication that it's efficient already is that it's the minimal cost or maximum probability. So that's sort of fairly correct, but that's only among the set that have these marginals. So the more general statement would be, do we beat, say, Bayesian inference? And the answer would be, well, if you're a teacher and you look at Bayesian inference, you can see that when they add up the marginals in the denominator, they don't match the costs. So you're doing this suboptimally from literally from a importance sampling standpoint. And so what you can do is introduce an importance reweighting. And that importance reweighting is exactly the Sinkhorn normalization. And then if you go and look again, it's still not there, and you can keep doing this. Sort of statistical justification for why you might do this. So in both senses, you would see that you are in fact more efficient, as efficient or more efficient, depending on your initialization. And the second thing being, which I mentioned in passing, but won't say anything particularly formal, is that Sinkhorn is a continuous function, right? And so then we can go back and ask questions like, what happens if we don't agree about the marginals? If there's some epsilon perturbation between yours and mine, or what if there's an epsilon perturbation on this M matrix, so that you have a different starting point than I do. And what we can do is sort of what you might expect is write proofs of continuity type, right? So if you have epsilon and you go to the limit, as those two become close together in the beginning, they can become close together. So what this kind of gives you is the sense that things don't totally fall apart, right? As we know, this is not the strongest guarantee, but it is, I think, well, it is the first mathematical result that I know of that gives anything of the sort. If you look at that literature that I mentioned, everyone just assumes this to be true and never looks back. So it's a nice demonstration that I think we can use the math that's out there to sort of make these stronger statements. Of course, there's much more. Many people have mentioned AVI, connection to algebraic geometry. Sinkhorn scaling has an invariant, the cross ratio, which is a homogeneous polynomial. If you're looking for the intersection of this variety with the linear constraints, there are large papers that Avi and others have written about that. We'll translate, of course, goes without saying. And so I think, the punchline here that I wanted to sort of end with is that I wanted to convince everyone that this is possible, right? We can write this down in math. There are interesting consequences for the starting point of the behavioral sciences literatures, but I think there are sort of much more, also there's potentially much more interesting directions in which we could lift more of the details of the kinds of problems and the models that people use into mathematical settings, and perhaps go forward there too. That's sort of a longer story than we have for today. So maybe I'll wrap there.
I had a question.
Is there a, oh, sorry, go ahead.
So you said you were gonna add some other structure to this, beyond these elements here. Is that what you said?
One can, right? So there's a question of, well, what's the right direction in which to sort of generalize, right? So like,
So that's, I didn't quite understand where you were going with it.
so one possible sensible choice is to say, well, this is a one-off interaction. We don't usually work in one-off interactions, right? We have sort of sequential interactions. So we might ask about sort of, well, what happens if you put them in sequential situations, right? And ask, do you retain certain properties of, say, Bayesian inference, like asymptotic consistency? And the answer is yes. So we've done that already. But more generally, you can sort of think about these as sort of multi-agent interactions that might also happen closer to real time. And of course, optimal transport gives you the tools to talk about those kinds of things also, right?
So what would I have to do to sort of generalize what you've got there? Just if you just give an instance of that.
So in the sequential case, it's actually fairly straightforward, right? So you start with some prior on the hypotheses, some fixed cost on the data. If it's sort of a teacher teaching someone, then after the first step, you pull out the row that corresponds to the data. That's your next marginal. And then you march it forward, right? And you just keep doing that. And so you're traversing
your cost and everything remains fixed.
Yeah, you're traversing a path on the manifold of cross ratio equivalent matrices where you change the marginals and go toward one of the corners. So that's one case. In sort of classic OT, the way you move from the way you introduce time is you induce a cost from an action potential. So this is usually done in sort of physical kind of context. And so that would be another. So those are a couple directions. There's quite a lot more that one can say, right? So another direction to go is to, well, think about these cost matrices and where they're coming from. So in machine learning and holistic modeling, we often think of distributions as having compositional structure. This is important in programming and other settings. Arguably, it's part of the way people think, right? Words and things they compose in some lawful ways, not some of them are quite complicated. And so then there's a question of, well, how to introduce that and deal with it in a sort of sensible fashion. Right? You sort of have a flat problem. But that's another possible direction to go in. A simple version of that would be, well, let's just stack them on top of each other and make a deep.
Yeah. I was going to ask if there's a analogous story. You had two agents. If you have kind of multiple agents all on the same footing, like no teacher, but they're trying to cooperatively reach a consensus.
Yeah, so I think this is an interesting question, right? So there certainly is such a story. The question of how precisely to formalize it and what the right things to sort of think about. I think as you suggest, coming to a consensus is one way to think about it. There's a bit of literature in economics about not coming to a consensus also. And these kinds of things. And so, yeah, these are interesting directions also. Or embed them on graphs or these kinds of.
I'd like to thank the speaker again for great talk.